Hello, I'm Steve Larson, an engineer at Cap Pumps, and today we're going to continue talking about cavitation. If you remember, in the first session we talked about cavitation, what it is and what it does to your pump. And in this second session we're going to talk about ways to avoid cavitation so we have a good, successful pump life. One thing to start talking about is the temperature of the liquid that we're pumping. So number one is temperature. Water, of course, is a liquid because of its temperature and pressure. And if the temperature of water rises, it takes more pressure to keep it in its liquid state. So therefore, if we're trying to pump an elevated water temperature, the closer we are to boiling, the easier it is to have it cavitate in your pumping chamber. In other words, if I'm pumping cold water, I could get down to -5 PSI inside my chamber and not have the water do any cavitation. But if I'm pumping up 160 to 180 degrees and I put -5 PSI in my pumping chamber, then I could start to see some cavitation. So temperature is very critical on knowing what kind of inlet pressures we need to keep the water liquid at all times. So number one recommendation on temperature is follow the guidelines on the pump specification sheets. The second thing we want to talk about is speed. The speed of the pump will determine how easy we can cause it to cavitate or not. All pumps have a rated maximum speed. If we try to exceed that, then we're going to be moving the plunger faster than it's rated for, and the areas to try to get the water in through the valves and the manifold will be exceeded, and we could cavitate. But let's just talk about how fast things are really happening. In a pump that's running at 1800 RPM, let's say, and if it's rated for that, that's fine. But what's happening is that plunger is going back and forth 30 times every second. So in 1 second at a time, like 1001, that plunger has to push out all the liquid and pull in a new set of liquid 30 times every second. So that's very, very fast. And that's why we don't want to exceed the speed rating on a pump, because if we do, it's going to be more susceptible to the cavitation. And the third thing we want to talk about is our inlet pressure. Again, cavitation occurs because we hit a low pressure regime during the pumping cylinder. So we want to keep the inlet pressure of the pump at all times within its rated specifications to avoid cavitation. This is one of the most overlooked areas that occurs because you may have a static pressure of one thing, but once everything starts flowing, the pressures will drop and you'll have acceleration losses in the lines as well. So we're going to draw up an example of a system here, and we're going to concentrate on that inlet pressure of our pump. So I'm going to draw a reservoir of water that we're going to draw from. And we got an inlet line here that leads to a pump that we're going to pump. Now, some of the things that we are going to do on our system is this water, let's say, is 4.6 feet tall, which is about right up to my chin. So that's how much water we have available to feed our pump. Our pump is a 10 GPM pump, and we have 5 feet of hose and 2 elbows in this line. So this is kind of our setup. Now, we want to figure out what size line do we need so that this all works correctly. Well, the other thing we need to know that we're still missing is what is the inlet pressure rating of this pump. This pump has a flooded to 60 PSI allowable inlet range. So what does flooded mean? Flooded means 0 PSI gauge. Okay, so we're going to use this information now to decide what size line is the proper size for this pump installation so that we avoid cavitation while we're operating. Well, if the minimum pressure is 0 when it's operating here, how much do we have to work with this inlet system? Well, you might think we have 4.6 feet of water. That's a lot of water. But in reality, that equates to 2 psi. So here at the bottom of the tank, we have 2 psi. And the lowest we can go is 0. So we have to find a line size that's 5 feet long with 2 elbows that drops less than 2 psi. So let's just start doing that calculation. Let's see, 10 GPM, maybe a ½ inch line will work. So we're going to look at a ½ inch line, and we're going to account for the line loss. We're going to account for the elbows. Then we're going to add them up, get a total, and then we're going to get a final pressure. All right? So if we look at charts and calculations that are available online or several places on the internet, we see that a 5-foot ½ inch line will drop minus 5 psi at 10 GPM. A couple of elbows thrown in there, we find out that they drop another minus 1.8 for a total loss of minus 6.8. Therefore, our final pressure, 2 minus 6.8, is a negative 4.8 psi. Now, it's pretty easy to see that that is lower than that. Therefore, this is not recommended. In fact, this is a lot of vacuum to pull because we're a third of the way to a perfect vacuum already. So this would not be recommended. So let's jump up to the next size, a 3/4 inch. And we look at the tables and we get, okay, this drops negative 0.7 psi. Quite a difference from a ½ inch line. A couple of elbows is another minus 0.4 psi for a total of minus 1.1, or a final of positive 0.9 psi. So we've made quite an improvement just from going to a ½ inch to a 3/4 inch line. So it's looking pretty good, but hey, let's just see what a 1 inch line does too. We put that in there, we look at the charts, we get that this drops minus 0.15 psi. The elbows drop minus 0.10 psi for a total of minus 0.25. Now we're at positive 1.75. So you can see the larger the line gets, the less pressure drop we have through this system. So looking at these numbers, I would recommend using the 1 inch line. We have very little loss through it, only 1/4 of a psi from beginning to end, and we're above our minimum, 0. Here at the 0.9, we're actually pretty close to it. So if you think about it, if you're on a mountain road and you're driving, do you want to drive over the edge of the cliff, at the edge of the cliff, or away from the edge of the cliff? I would choose this one. That way it gives us the less likely for any cavitation to be present. Another thing that one can look at, and you should do it concurrently with your line loss, is what's your flow velocity. A proper flow velocity on a suction line, whether it be pressurized or gravity feed, should be 4 feet per second or less. So let's see what our velocity is. Doing the calculations using the line diameter and the gallons per minute and the flow, a ½ inch line is 16 feet per second. A 3/4 inch line is 7 feet per second. And a 1 inch line is 4 feet per second. So there we have both conditions met for a good inlet condition. And I would recommend doing both conditions, because even though you could have 4 feet per second in the inlet line, you could have too big of a drop if the line was really long, or you used multiple elbows and twists and turns, which everything adds to the pressure drop in that line. So when you're sizing an inlet, it's very important to know your starting pressure and your line losses to make sure your inlet pressure on your pump is within the guidelines.